So we're ready for calculus with the relationship between continuity and differentiability. And there's a very important idea or premise that is that you need to know for this section. And you will write it down at least 1 point on the AP test. Basically what we need to do is establish if things are continuous. Does that necessarily mean that they're differentiable? Or vice versa. If something is if it's differentiable, is it automatically continuous? So we're just going to investigate a few things. So the first premise is we have a square root function. We're just going to answer these following questions. So on the grid, they just want you to graph this. I don't know how. I mean, you could even just plot points. Like when you plug in -2 squared is 4, minus 4 is 0. The square root of that is 0. Plug in 0. Well, if you do 0 minus 4, oh, we're square rooting a negative. Can't do that. We could have the same value at 2. You could try, what would be another good one? I think 3 squared is 9 minus 4. That's not a good one. 4 squared, 16 minus 4. That's not even a good one. Let's just use a calculator. Okay, there it is. So go to your graph, look something like that. Now here's the thing, is your graph does not understand, a graph and calculator will not only do the vertical line test, it does hit at -2 and it does hit at +2. So don't freak out about that. But these are not perfect answers by any means. So we have the general graph. Now let's go back and show what that looks like. If you want the best graph, you could actually look at your table as well. Where's my table at? Got to find my calculator first. So second table, you can see 0, -2, it is defined, it is 0. And then you can see these other values. And you could plot it better than what I have drawn. But anyway, if you look at your calculator, is f of x continuous at x equals 2? And I just want you to explain. Well, let's look at our three-part definition. So at x equals -2, what's the limit as x approaches 2 from the right of f of x? Okay, well that equals 0. But what's the limit as x approaches 2 from the left? Well, it's not getting closer and closer to anything, so that limit does not exist. So can it be continuous? Well, it is not. So this is discontinuous, or not continuous. And you can just say, even though the function is defined, or even though f of x equals 0, or sorry, f of 2 equals 0, which is the same as the limit from the left, I would just say the limit as x approaches 2 of f of x does not exist. Now, really the similar question, well, what about the derivative of that? And that's kind of why you didn't see is there's no slope at that point. If you try to draw a tangent line, well, where would the tangent line for a point be? Well, how about this? Let's just differentiate it, and maybe that'll make more sense. So following our chain rule, you would bring the 1/2 in front. X squared minus 4 is now to the -1/2 power, times the derivative of the inside, which is 2x. That'll cancel out this 1/2 and the 2. So we're looking at x over the square root of x squared minus 4. And now when you plug in 2, so let me switch back to green. So f prime of 2 would equal 2 over 0. Oh wait, that's undefined. So analytically, the derivative does not exist here. So it was not continuous, and it was also not differentiable. Oops, I thought it was further down this page. Well, what if we looked at this function, x to the 1/3 plus 2 at x equals 0? Well, if we look at this using a graphing calculator, we can sketch it over here to the right. We're at 0. I think if we plugged in 1, well, 1 to any power is to 1 plus 2 is 3. I think it makes sense that it's a cube root function, so it kind of looks like this. Same thing over here. So based off our limit definition, let's go a little bit faster. This is continuous, and what we're looking at is I already forgot what I was writing. The limit as x approaches 0 on the left side of f of x is equal to the limit as x approaches 0 on the right side of f of x, which is equal to f of 0, which they all equal to. Pretty quick explanation there, I think, but you have your three-part definition. But if we talk about the differentiability at x equals 0, what we get is, well, again, let's just do it analytically. So let's find f prime of x, which is 1/3 x to the negative 2/3 power, which, as a reminder, that's 1/3 cube root of x squared. So what's f prime of 0? Well, what we're looking at there is 1/3 times 0, which I think you would all agree is undefined. So what we have now is a case where a function is continuous but not differentiable. So not differentiable. And I hope that makes sense, because if you were to look at the tangent line here, and I did a poor job drawing it, if you tried to draw a tangent line, it would be a vertical tangent. And maybe a graphing calculator would give that more justice than how I drew it. And we have one more example. And we have I think we just one more. And maybe I'll just use a calculator here because I don't want to confuse you any more than maybe I already have. So we're looking at x to the 2/3 power plus 2. If I go to the graph of that, you can see we have a sharp turn or cusp right there. Something like that. So it's another problem that is continuous at x equals 0. And so yes, go through your three-part definition. Limit as x approaches 0 on the left side of f is equal to the limit as x approaches 0 on the right side of f, which is equal to f of 0. So that's a y value of 2. But again, if I asked you for the derivative of this, and bring that 2/3 in front, x to the negative 1/3 power, which is equal to 2/3 cube root of x. And then if I were to ask you for f prime of 0, oops, forgot to write x, I guess. We're looking at 2/0, which is undefined, so not differentiable. So the premise that they're getting at is you can be continuous without being differentiable. But, so does continuity imply differentiability? No. So the thing is, if something is differentiable, that means that it's all a smooth curve. In other words, there are no sharp turns. You know, there's no vertical tangents. I'm trying to think of anything else off the top of my head. So with all of that, we can say differentiability the ability to be differentiable implies continuity. That is very important. Remember earlier in the year we talked about the intermediate value theorem only applies when it's continuous. And they might not tell you it's continuous, but they'll tell you it is differentiable. Well, differentiability implies continuity. So let me jump to that. I just want to give you the answer key. You can pause the video and write down anything you want. By the way, sometimes they're called cusps or nodes that have sharp turns. And you can talk about graphically a function is not differentiable if the function is not continuous. A point of inflection. Now you got to be careful with that statement. I'm not a big fan of how he says, because there are points of inflections that are differentiable. Because polynomials are always continuous and polynomials have points of inflection, so I don't like that he said that. But a cusp or a node is not. All right. So in order for a function to be differentiable, the limit, well, first of all, the function must be continuous. That's a given. The limit as x approaches a on the left side of that function, function's derivative must equal the limit as x approaches a on the right side of the function's derivative, which means that the limit as x approaches a of that function's derivative must exist, which is going to bring me to what I perceive to be some fun problems. So, first of all, is a function continuous at x equals 3? Well, we did that earlier. We plugged in both 3's into these. So you want to make sure that the limit as x approaches 3 on the left side of this function, and analytically, that's the square root of 3 plus 1, is equal to, well, the square root of 4 is 2. Double check that that's the limit as x approaches 3 on the right side. And analytically, that is just 5 minus 3, the right side, which is also 2. And we also, so those things are equal. That means the limit exists. So x approaches 3 of f of x is equal to 2. And also don't forget to mention that that is equal to f of 3. Why? Because x is defined. It's the same work as right here. Okay, so it is continuous. What about differentiable? Well, if it's differentiable at that point, that means that we have to find the derivative of each piece. So the limit as x approaches 3 on the left side of the derivative, so you could actually find the derivative of that, would be 1/2 x plus 1 to the negative 1/2 power. And as a reminder, plug in 3 in there, plus 1 is 4. This is the square root of 4 is 2, but it sticks into the denominator times the other 2. So we're looking at 1/4. I hope you can do that in your head. Well, if you look at the limit as x approaches 3 on the right side, well, analytically, the derivative of this is just negative 1. So that slope is negative 1. So this is not differentiable, and your quick analysis is saying that the limit as x approaches the left side of 3 of f prime of x does not equal the limit as x approaches 3 on the right side of f prime of x. I'm going to give you a quick visual of what's going on, by the way. So if I asked you for the graph of the piecewise function, shifted up 1, isn't it up 1? Nope, it's left 1. Sorry about that. So we have this curve until we get to 2. No, until we get to 3. All right, and it's defined right there. And then when we get to the other function, 5 minus x, it's a function that looks like this. Well, there's definitely a sharp turn right there, so that is not differentiable. So if you look at the graph of that, it definitely does not work. I was supposed to stop it at 5 though. Sorry about that.